Thanks, and thanks to all the organizers for the invitation. It's been a great simulating conference. Yeah, I'll be talking about some work done with these folks. Jacob and Yizhen are two postdocs, and Weicheng and Shengxi are two PhD students. Okay, so let me start out with some context for this work. So Hilbert space is very big, as you all know, and depending on which community you're from, you might be interested in different properties of quantum states, right? So for example, condensed matter physicists might be interested in asking questions of do states have local order or topological order, whereas computational complexity theorists might be more interested in asking how random states are, or how difficult they are to simulate classically. And correspondingly, to probe these aspects, one needs diagnostics of increasing complexity, right? So for example, for local order, it's pretty simple. Just a local order parameter usually suffices. But then you need things like entanglement, or even sampling a wave function in a given basis, right? So I guess in the spirit of this conference of trying to bridge together these two sides of computational complexity and condensed matter physics, quantum information, this talk is about an intermediate property, sign structure, which clearly has computational roots, but is also physically relevant. Good. So I think most of you are probably familiar with sign structure, sign problem in the context of Monte Carlo simulations. It's a major headache for anyone doing Monte Carlo. But is it simply a computational complexity problem, or is there something more physical about it? For example, let's say I take a high temperature superconductor phase diagram, right, and much of which is inaccessible to efficient numerical simulation. Is it just our lack of imagination for simulating it, or are there actually distinct physical properties of the phase diagram that distinguish it from, say, sign-free states? So given that sign structure is physically significant, what are its manifestations? How do you detect a sign-full wave function as opposed to a sign-free one? As you probably know, sign-free wave functions can already realize a variety of phenomenon, topological order, quantum criticality, even these good LDPC codes we've been hearing about. So exactly how does the sign-freeness constrain the properties of a sign-free wave function? Okay, so let me just say a little bit more about sign structure first at the level of Hamiltonians. So ideally, Monte Carlo simulations require some local basis in which these matrix elements are negative. And this allows one to map to some classical partition function that can be sampled. And this question of whether or not such a local basis exists already suggests a connection to gapped quantum phases of matter, which are defined as equivalence classes up to these local basis changes, right? So this naturally suggests a question, I think, first posed by Matthew Fisher, asking, are there quantum phases of matter in which there's an intrinsic sign problem, in which there's no such local basis change, no such local unitary that can give you this property in which these are negative, right? So in this case, the sign problem would really be a feature of the entire phase of matter, not just a particular representative Hamiltonian. So remarkably, it turns out that it appears that there are such phases of matter with intrinsic sign problem. Hastings showed that every commuting projector Hamiltonian with double semi-on topological order has a sign problem. So it's really a property tied to the double semi-on nature of the topological order. And one can ask similar questions about the ground states of local Hamiltonians, not just the Hamiltonian itself. One can ask, are there ground states in which there's no local basis change that will remove all the signs in the amplitudes of the wave function. If so, we would say that the ground state wave function has an intrinsic sign problem. And this is even stronger than that of a Hamiltonian, because an intrinsic sign problem at the level of ground state implies that any parent Hamiltonian of such a state also has a sign problem. So this is just to motivate that sign problem is not just a computational question, it's deeply tied to physics of matter. So this now begs the question, how do we detect sign structure, okay? Or even the lack thereof, right? So it turns out that for one-dimensional non-negative or sign-free states with zero correlation length, Hastings has a very nice proposal for how to detect the sign-free nature of this. Okay, so what he suggested was basically take the wave function, then measure pretty much the bulk of the wave function in the basis in which this state is non-negative, say the computational basis. Then what he showed was that after measurement, due to the sign-free nature, the resulting entanglement between the two remaining pieces must be very small. It must decay superpolynomially with their separation. Okay, so in other words, for a sign-free state, at least with zero correlation length, measurements are unable to generate much correlation. Okay. And one picture for this is the following. Basically, such a sign-free state with zero correlation length can be approximately thought of as a coherent give state. It's basically a state in which these amplitudes are given by Boltzmann weights of some local classical Hamiltonian. Here, the locality follows from the zero correlation length assumption, and the classical part follows from the sign-free condition. And once you accept this picture, then it's clear that measurements in the classical basis cannot generate entanglement. What the measurements are doing is basically fixing a classical configuration in the bulk, and once that happens, the remaining state is separable. It just depends on the local Boltzmann weights on the two sides. So I'll refer to this type of diagnostic as measurement-induced entanglement, or MIE. And I should point out that a similar diagnostic was proposed way back in 2004 by these people. It's called localizable entanglement. Okay, so this is a very interesting probe of sign freeness, at least if you enforce a zero correlation length condition, right? So most of this work is just how do we detect sign structure more generally beyond zero correlation length. We'll be interested in particular in quantum critical states in which the correlation length is actually effectively infinite. Right? So the central proposal is that for a sign-free state, entanglement induced by measuring in the sign-free basis must decay at least as fast as existing correlations before the measurements were made. Okay, so I should admit that we cannot prove such a statement in full generality, but we can have very sharp results in several settings of interest. So first, we can show that for a stabilizer state that's sign-free, the measurement-induced entanglement is upper bounded by mutual information. And this allows us to place constraints on many of the dynamical steady states we've heard about this week. These hybrid circuits and measurement-driven criticality. And furthermore, we can show that for a sign-free qubit wave function, if A and B are two qubits, then the measurement-induced entanglement is upper bounded by a simple two-point correlation function. And this allows us to constrain the ground state of critical Hamiltonians. In contrast, if we see violations of these bounds, then they're direct signatures of non-trivial sign structure of the thing we're probing. And I'll give you some examples of that. Okay, so now let me just get the definition clearly across. So we start out with a pure state, and we try partition it into A, B, and C. And we'll want A and B to be small intervals that are far apart, and C to be everything else. Then the measurement-induced entanglement is defined as follows. So we perform measurement on C in a given basis, a given local basis. And we obtain outcome little c with some probability PC. And after we get that outcome, the remaining system AB is now in some pure state that depends on the outcome we got on C, right? And SA is just the von Neumann entropy between A and B for that pure state on AB we got. So MIE is just the average entanglement you generate after measuring C in a given basis. And we'll want to compare this with things like correlation functions between A and B or mutual information between A and B. Okay, so let's move on to the first part of this talk, which is just what happens for stabilizer states. What can we say about them? So first, it's not too hard to convince yourself that for sign-free stabilizer state, one can choose all stabilizers to consist of purely X-type or purely Z-type. So this is a CSS code, okay. Such as toric code. One more non-trivial property that we found is that the MIE between two regions A and B is upper bounded by the mutual information when you measure the complement in either of the sign-free bases, so either Z or X. So let's first get a little bit of intuition for this result from some toy examples, very trivial ones. So say I have 3 qubits, A, B, C, and A and B are in some bell pair and C is decoupled. Okay. Then the mutual information between A and B is 2, and measuring C clearly does nothing to A and B, it's decoupled. So the induced entanglement is just the entanglement that was already there, which is 1 bit, right? A more non-trivial example is a GHZ state. So now the mutual information between A and B is 1. And now if I measure C in the X basis, then I create a bell pair on A and B, and so that's 1 bit of entanglement. So this bound at least checks out in these 2 simple cases. And of course, if I measure C in the Z basis, then I collapse the cat and I get 0 entanglement, satisfying the bound. So remarkably, it turns out that this toy examples are pretty much all we need to prove this statement in full generality for all sign-free stabilizer states. And that's because there's a very nice structure theorem for stabilizers that says that any stabilizer on A, B, and C is equivalent up to local unitaries on A, B, and C to just a direct product of GHZ states, bell pairs, and product states. So we need to refine the structure theorem a bit. So what we show is that if you further assume that the stabilizer state is sign-free, then these local unitaries can be shown to be sign-free preserving. So they'll map Z-type to Z-type, X-type to X-type. And what this is good for is that then these unitaries will commute with the projective measurements we're doing on the C system, right? And that allows us to map the whole calculation of MIE on the left-hand side to that on the simpler right-hand side. So pretty much we only needed to do the previous slide calculation. And yeah, and as I convinced you on the previous slide, this proves the bound we want. Okay, so as a brief aside, let me remind you of an example of a non-sign-free stabilizer in which you do get measurement-induced entanglement even though you have 0 mutual information. That's the well-known cluster state, let's say in 1 dimension. So this has 0 correlation length, and 2 qubits far apart have 0 mutual information. However, if you measure Z everywhere except for these 2 qubits, then, well, due to many reasons, for example, due to the string order parameter in this cluster state, you can see that you generate 1 bit of entanglement after doing the measurement. So this is an illustration of how the sign structure can, well, violate this bound I showed earlier. And in fact, we use this property to show that this cluster state has what we call the symmetry protected sign problem, one that no symmetric finite F circuit can unwind. Okay, so let's try to apply this bound to these dynamics of interest we've heard about a lot this week. And that's these hybrid quantum circuits, which involve both unitary dynamics and projective measurement. So it turns out that even without unitaries, with measurements alone, you can generate interesting critical steady states. One simple model of such a measurement-induced critical point without unitaries is the following. So let's say we take a 1D chain of qubits, and with some probability we measure nearest neighbor ZZ, and with some probability we measure X. Then the ZZ measurements want to fuse everything into a big GHZ state, whereas the X measurements are just poking holes and want to decouple it into a product state. And so it turns out that when these two operations are done with equal probability, one is at a critical point, and this type of circuit generates a steady state consisting of a direct product of GHZ states with some power law distribution in their size. Okay. So much more can be said for this dynamics. For our purposes, it's just important that it's sign-free dynamics. It's a CSS code at all times. And moreover, it's a very simple sign-free dynamics. It's just a direct product of GHZ states at all times. Okay. And due to this very simple structure, we can just see easily that the mutual information between two qubits is non-zero only if the two qubits belong to the same GHZ cluster. And similarly, the measurement-induced entanglement between the two qubits is non-zero for the same condition. So we expect that the MIE and the MI should track each other very closely for this steady state. So for such dynamical, for any critical point with conformal symmetry, it's convenient to plot every quantity against what's called the cross ratio. This is a ratio of these chordal distances in this geometry. And so we can plot all the quantities of interest, MI and MIE, against this cross ratio for such a critical steady state. And indeed, we find that the MI and the MIE measuring the X basis closely track each other. And the MIE and the Z basis decay is much faster. So this is all consistent with this, this bound between MIE and MI for sign-free stabilizers. So this is a pretty simple dynamical system. One can imagine more intricate dynamics. So for example, the ZZ and X measurements, if you do a Jordan-Wigner, map to fermion parity measurement of neighboring Majorana's, right? However, one can consider, instead of measuring parity of 2 Majorana's, you can measure parity of 4 Majorana's. And now the dynamics is more complicated, right? However, so based on numerics, we find that this still leads to some conformally invariant critical steady state. And moreover, this type of dynamics is still sign-free. If you Jordan-Wigner back to spins, it's just ZZ and next nearest neighbor XX measurement. Okay. So we still don't have a handle in understanding this dynamics of this interacting model, but again, our general constraints for sign-free stabilizers still applies. And we find a similar story that MI and MIEX track each other, and overall this bound is obeyed. Okay. So this bound can be put on a slightly more formal setting. So what these authors found was that the MIE and MI power laws are actually given by these quantities, which are the lowest scaling dimensions of certain boundary condition changing operators. It's a long story. Briefly, in evaluating entanglement in these circuits, it maps to some free energy, change in free energy of the conformal field theory when you change the boundary condition. And yeah, I encourage you to look at this paper if you want more details. But we can simply just translate our result for this bound on sign-free stabilizers to a bound on these scaling dimensions. So I think it's quite interesting that that sign structure, which is naively a UV property, is placing some kind of constraints on the IR physics here. Okay, so that's a story for sign-free stabilizer dynamics. And what about dynamics with sign structure? So as many of you probably expect, if we restore the random unitaries to these type of protocols, then we'll generate all sorts of signs, right? And so we can go back and consider the original entanglement phase transition between the area law and volume law phase. And let's start out with that of the Clifford unitaries with single qubit measurements. So what we find is that the MIE now decays with a much slower power, 0.43, compared to mutual information, which is around 2. Right. So in this case, the MIE is much more long range than MI, which is a clear violation of the bound on the scaling dimensions. Right. So this is a direct signature of the signful nature of this hybrid critical point. And it's tempting to conjecture that this critical steady state has an intrinsic sign problem that no finite depth local unitary can remove. And so it'd be interesting to try to prove such a statement, because it'd be a first example of a critical state in 1D that has an intrinsic sign problem. We can also consider the Haar hybrid circuit. And as you know, the Haar sign structure is literally more complex than the simple Clifford signs of plus or minus 1, plus or minus I. So we expect that here the MIE should be even more long range than the MI. And indeed, that's what we find. So for this hybrid transition, the power is 0.29, which is even slower than that of the Clifford power law. So yeah, so let me just point out that the mutual information is unable to distinguish the two transitions, right? It decays with the same power for both Haar and Clifford phase transitions. But here the MIE provides a way to distinguish the two classes. And there's the intuition of sign structure behind it. Okay, so that's the story for implications of sign structure for dynamical steady states. And now I want to return to more conventional systems, just ground states of local Hamiltonians. So for that purpose, we prove a very simple claim. And the claim is that if psi is a non-negative wave function in the z basis, and if A and B are single qubits, then the measurement-induced entanglement between A and B measuring everything else in the z basis is upper bounded by a simple 2-point function, the XX correlation. And this is inspired by this localizable entanglement paper. So the proof is quite simple. Let me just sketch it out here. So here's our assumed sign-free wave function in the computational basis. Then following the localizable entanglement paper, it's useful to consider as an intermediate step, not measurement-induced von Neumann entropy, but measurement-induced concurrence, which is a good measure of entanglement for qubits. And so the concurrence is defined as this expression in absolute value here. So yeah, so this is a measurement-induced concurrence, and we can just plug this positive or non-negative wave function in, and we get this expression. And now the non-negativity of the wave function really comes in, because what it means is that this first part doesn't contribute any phases, and all the minus signs are coming from this matrix element here, right? So this means that the most that this absolute value can be is if these phases contribute coherently, or in other words, if we replace the y's by x's, right? So what we get is that this is upper bounded by this expression with the x's, and this is nothing but the 2-point XX correlation function. So this shows that the MIC is upper bounded by the 2-point function, and it turns out von Neumann entropy is upper bounded by concurrence, so we get the desired inequality. So now I'd just like to apply this result to some of our favorite spin chain models and see what they imply. Right. So let's go back to our old friend, the transverse field Ising model in 1D. So this is the model, and we're interested in the ground state at the critical point. And we'd like to see how MIE and MI all behave for this critical ground state. So here I've plotted the 2-point XX correlator, MIE, MI, and MIE in a different basis versus the distance between the two qubits A and B on a log-log plot. And as you can see, the MIE, they all decay slower than the XX correlator as expected. Okay. So what was kind of surprising is that when we relax the condition that A and B are single qubits, when we allow A and B to vary in size and in their distance, then the MIE appears to be only a function of the cross ratio of the geometry. So in other words, the MIE appears to be a conformally invariant quantity, which at least we still have some trouble rationalizing. So as a point of comparison, we also looked into what we call forced measurement-induced entanglement, where you don't average over all the outcomes, but you enforce a particular outcome on C, say a uniform configuration, and then you look at the induced entanglement. And so the FMIE also decay as power laws. They're functions of the cross ratio only. And those one can understand fairly easily because those do correspond to known conformal boundary conditions of the CFT. However, the MIE involves this averaging over boundary conditions that's like kind of tying together different replicas. And that's still a rather mysterious point for us that we're trying to understand. Yeah, so just to summarize this point, we found that MIE is a function of the cross ratio only, but there's still a question of how to understand this generalized conformal boundary condition. Okay, so that's just some applications of this bound to simple sign-free spin chain models. Now, what about for critical ground states with sign structure? So for that, we decided to explore a very interesting class of states called Gapless SPTs, pioneered by many people in the audience. And these are, as the name implies, gapless analogs of SPTs. So one simple example of this is a transition between the 1D cluster state SPT and a ferromagnet. Okay, so these gapless SPTs are very interesting. They have gapless edge modes coexisting with bulk criticality, and they're protected by a global symmetry. And again, much more can be said, but for our purposes, it's just important that such critical states are neither sign-free in the X nor the Z bases. Okay. So what happens when we probe such a sign-full state with this MIE diagnostic? So here we find a very different behavior. So in this case, the 2-point functions, mutual information, all decay as power laws, as expected, due to the critical nature of the state. However, the MIE is now infinitely long-range, right? And that's because the MIE is basically inheriting the gapped cluster state property, right? So one can again define a string order parameter that basically enables this MIE to be infinitely long range. Okay. So in this case, the MIE does not decay faster than slowest correlation, and this is a direct signature of the non-trivial sign structure. And furthermore, it's very likely that this gapless SPT also has a symmetry-protected sign problem, like its cluster state counterpart. Okay. Yeah, so that's pretty much all I wanted to say. Let me just conclude with some open questions. So first, as I said, it would be nice to prove rigorously that this hybrid Clifford circuit transition has an intrinsic sign problem. Since it's within the realm of stabilizer states, such a proof might be possible. It would also be interesting to find any critical ground state of a local Hamiltonian with an intrinsic sign problem, in particular in 1D. Is that even possible? And it would be interesting to further explore how this MIE, the sign problem, are encoded in the IR or CFT data of describing the state. How to think about these conformal boundary conditions, right? And finally, I guess more related to this conference, it'd be good to further explore how this MIE sign problem are related to classical hardness of sampling. So let me just present the main conclusions, and yeah, thanks for your attention.
Yeah, thanks for the nice talk. I wanted to ask a question about the gapless thing you're showing at the end there, this cluster state transition point. So there's like this paper by Hsieh, Chen, and Zhaogang Wen from a while ago, and looking at basically this model, and it has this like MPO or local unitary symmetry times the Z2 times Z2 with a some anomaly like an H_3. Do you know if there could be some connection between that symmetry of the ground state and the sign structure? Like maybe you could prove if you are a fixed point under the symmetry, you have to have non-trivial sign structure.
Well, you're saying this gapless SPT has some enhanced symmetry beyond?
Yeah, from being at like a critical point.
Yeah, possibly. I'd have to look at that more carefully. I think in this case, the non-trivial sign structure is more related to the different conformal boundary condition for this critical theory.
And maybe I could ask
but maybe that's also related to this enhanced symmetry too, right?
I ask some more general questions. I guess the double semyon example came up, and that has some similar kind of H_3 co-cycle going on. Not the same one, but kind of in the same vein. Is there any known relation between like algebraic structure and having to have a sign problem? Like if you have some certain symmetry under an algebra that has like this anomaly?
Yeah, not that I know of.
Okay, sorry. Cool. Thank you.
So does being intrinsically non-CSS imply that there is this intrinsic sign problem?
Well, no, because I mean, if you restrict to Clifford unitary to unwind.
No, I mean intrinsically non-CSS, as in you cannot apply a finite depth like circuit to get rid of the non-CSS nature of the stabilizers.
Right. And you're saying what that implies?
So if it is such an intrinsic non-CSS stabilizer state, like double semyon, then whether that already implies that there is an intrinsic sign problem.
I think it's suggestive, right? Because you're kind of restricting the target state to the only stabilizer type, right? By imposing that, right?
Yeah, it's only stabilizer.
Right. So I think it's suggestive, but it doesn't immediately imply it. Right?
Yeah. So for the hybrid circuit problem, like it seems like the steady state is more likely to be some intrinsic non-CSS state, and maybe.
Yeah.
Right. So.
Right.
Okay.
Yeah, I think that probably can be that's more doable to show, right?
Right.
As opposed to the just proving completely that's intrinsic sign.
Mm-hmm. Thanks.
Sure, yes. Hi. So you showed these nice probes for detecting a sign problem, or at least, right? You can get a positive signature for the presence of a sign problem.
Right.
Can you envision a probe that's agnostic about a basis choice? Because, for example, the cluster chain, as you mentioned, has a sign problem in that particular basis, but it has a sign problem free basis. Can you comment?
Right. Yeah, I think it's a very good question. So basically, as I said, we were interested in the zeroth order question of just probing, consequences of sign freeness in a given basis. But I think you're getting at how to probe the intrinsic sign problem itself, right? Yeah. So we've been trying to think about that a bit. Maybe one needs to consider MIE, with doing measurements in a random local basis, right? And then maybe looking at the average over that. Then it gets pretty complicated, but yeah, we have some ideas like that.
Thank you.
Hi. how rich is the class of sign-free states? Can you, for example, have a volume law? I mean, I guess you could in certain trivial ways, but you know, what's known about this class of states?
Yeah, so I should have mentioned, I didn't have time, but I should have mentioned this work by Matthew and Tarun from a couple of years ago. So what they find is that basically the sign-free states do not generically give rise to volume laws. You can have fine-tuned ones, like long-range triplets, for example.
Right.
Yeah, I think the moral of their work is that you need sign structure to have like, generic volume law states, right? Yeah.
Thank you.
Any other question?
The microphone on. This kind of reminds me a bit of like strange correlators, like an entanglement-based strange correlator.
Yeah.
I wonder if that could potentially answer Dominic's question about what's the relation between like, anomaly and...
Yeah. I think there's definitely a close relation between strange correlator and forced measurement-induced entanglement, right? Because the strange correlator is you're taking an overlap with a particular product state, which will convert into that forced outcome that you're considering.
Like
so,
on average, if it's this right symmetry, you probably have a same kind of property in your strange correlator for any random. You're measuring like something that this sign here.
Well, okay, so at first we were hopeful that the forced MIE could already be enough for our purpose, but it's actually quite tricky. So even for the sign-free critical Ising ground state, if you force a particular measurement outcome, you can actually generate a Bell pair that's arbitrarily long range in that case, right? Which is, yeah. So that's very different from the average MIE behavior, which decays, at least as fast as the given correlation. So somehow like given outcomes can be anomalous. And that really kind of motivates us to consider the average MIE.
Okay, so any last question? If not, let's thank the speaker again.